Swayam Prabha. Digital India. Educated India.
So we'll continue from where we completed in the last two lectures. What we have seen that the first lecture we had seen four fundamental subspaces corresponding to a given matrix, and their dimensions. So that was the goal of the first lecture. In the second lecture, we had seen the geometry between the fundamental subspaces. That's the orthogonality, and we had also one application of that in the projection or in the least square approximation, right? So today we will see the third part of fundamental theorem of linear algebra. What is that? So basically here our goal is to, given any matrix, not only the square matrix, given any matrix of size m by n, we want to diagonalize the matrix, or we want to decompose it into sum of some very simple matrices, so that we can use that matrix in different applications. Okay, so that's our goal. For that, so we have seen the fundamental subspaces and their dimensions and the geometry. So the overall, given any matrix A and any row, any vector x in the space Rn, we have seen that Ax is going to the column space of the matrix, right? Ax, given any matrix A and x vector which is in Rn, so this belongs to some vector b. This is equal to some vector b, or I shouldn't say equal, but so we are getting a mapping between the this Rn and the column space of the matrix, right? So, but this mapping, you see that it's not really an explicit mapping. So what we want to do, we want to make this mapping more explicit, in the sense that we'll be choosing some kind of orthonormal basis vectors from each of the fundamental subspaces, the four fundamental subspaces, and show an explicit relationship between them. So for example, you can see in this picture, so we are choosing some kind of vectors v1, v2, vr, and then vr plus 1 to vn, total n vectors from Rn. So similarly, so we are showing that they will be mapped to some particular vectors. The explicit mapping will define by which we will be able to diagonalize the matrix. We can write this into that diagonalization from which will be giving us the SVD, or singular value decomposition. So this is we want to learn how we can write this. We can obtain these orthonormal basis vectors corresponding to each of the fundamental subspaces. So that's the last part of your fundamental theorem of linear algebra. Okay, so we'll be here in this the final part. We'll be making an explicit mapping by Ax is equal to b, whatever we have seen. We'll make it more explicit or more clear. Okay. So for that, we need to understand little bit of eigenvalues and eigenvector. But eigenvalues and eigenvectors are defined for square matrix, only for square matrix, right? But we want to make this video for general matrix of m by n. But before that, we need to study eigenvalues and eigenvectors, because that will be giving us some idea of how to do that. Okay. So how many of you already have studied eigenvalue, eigenvector? Most of you. So I'll go over this part very quickly. I'll not go into the proofs of all these properties what I'll be stating. So here also the eigenvalues and eigenvector, our goal is to diagonalize but diagonalize the square matrix. Okay, so you want to diagonalize the square matrix. What are eigenvectors? Just some special vectors. When you apply this matrix A on that vector, so its direction remains unchanged, either in the same direction or it may be reversed, but it will be aligned with the same vector as X. Okay, so those special vectors. So not all the vectors will preserve this property, right? Some special vectors in Rn, because we are considering A as n by n matrix. Okay, some special vectors from Rn will remain, will preserve this property of the direction when we apply the matrix A. So those special vectors are called the eigenvectors. And we can then write Ax is equal to some scalar into that vector x. That scalar will be called the eigenvalue. So that scalar will actually say that whether the vector x will be stretched or shrink, or it will be remain same, or its direction will be reversed. So that will be determined by that scalar lambda. So more mathematically, if we go, so we can say that Ax is equal to lambda x. We can write this as system of homogeneous equations, right? System of n homogeneous equations with n unknowns, right? And when this system has we know that this system will always has a zero solution. Zero vector will always the solution of this system. We are not interested in the zero vector when we are considering the eigenvector. Eigenvectors, whenever we define, we say that these are non-zero vectors. So when this system will have a non-zero solution, in which case it will have the non-zero solution. Yes, its determinant should be 0. Why determinant should be 0? When we are talking about some homogeneous system, you go back to your fundamental theorem. So this is a matrix. This is the first the row space. This is the null space. Now we are talking about this matrix, right? A minus lambda I. Right. So this is the null space of this matrix A. A minus lambda I. Now when this null space of this matrix A minus lambda I will have more than 0 elements. I mean 0 elements, in addition to that the more elements. When the column vectors of this matrix are dependent. So that's our definition, right? When the column vectors are dependent, so that means that this null vector will have. Is that okay? So we have discussed this in the last lecture, if you remember. So if the column vectors are independent, then this null vector will be only 0 vector, right? So when they are dependent, then null vector will have 0 vector. In addition to that, you will have some non-zero vectors. Okay, so when the column vectors are dependent, then determinant will be 0. So that you know that the property of the determinant. So first, basically, so this equation, determinant of A minus lambda I, will give us the values of lambdas for which we need to what will be giving us the eigenvalue. So this will be a polynomial so this will be a polynomial of degree. This will be a polynomial of degree. So this determinant of A minus lambda I, what will be the degree of this? So this will be a polynomial in lambda. So if you expand this for only for 2 1 minus, so I have a matrix 1 1 2 2. So then I find this determinant of A minus lambda I equal to 1 minus lambda 2 minus lambda. What will be the degree of this polynomial? 2, right? So if you just expand this, you'll be getting some constant, say A0 into lambda square plus A1 into lambda plus right? So similarly, if you expand this n-dimensional determinant, so you will be getting a polynomial of degree n. So this is called the characteristic polynomial, and the corresponding equation, this determinant of a minus lambda is equal to 0, is the characteristic equation. So we first solve. So to find the eigenvector, first we need to find the eigenvalue. So that should be your first step. So when you find some eigenvalues, then only we can compute the eigenvector from the equation what we have given in the definition. So first we compute the eigenvalues. But one thing you should notice here, in general, when we solve this characteristic equation, the eigenvalues may not always belong to the real domain, right? It could be also complex number. So we say that this will be in some algebraic extension of the real space of real numbers. So the second step will be we compute the eigenvector by putting the values lambda in this equation, right? So you know that how to what actually we are getting. So basically, corresponding to each lambda, we are solving this system of homogeneous equations to find x, right? To find x. So what is actually we are computing here? We are computing the when I think we discussed how to compute the spatial solutions of the system of homogeneous system of linear equations, right? How did we compute it? You remember? We computed the pivot variables, p variables, and corresponding to each p variable, we computed the spatial solutions. And those spatial solutions, if we take the linear combinations of those will be giving us the space corresponding to that. This lambda will be getting that corresponding to that lambda will be getting that space, which will be called the characteristic subspace. Okay, so basically we will be computing all the spatial solutions and take their linear combinations to get the characteristic subspace. Okay, so we'll discuss that corresponding to one particular lambda, we can have more than one eigenvector. Although corresponding to one eigenvector, we'll have unique eigenvector. Okay, so those two properties we'll see in the next slide. Okay, so just to recap your previous, can you try to compute this the eigenvalues of this matrix? So let's go try to do this 1, 3, 4, 5. Okay, so we first solve the characteristic polynomial, which is determinant of a minus lambda I equal to 0, which is equal to 1 minus lambda 3, 4, 5. Okay. Lambda square minus 6 lambda plus 5 minus 12. So what will be the lambda? Minus 1 and 7. Okay. So then you have to do what you have to do. You have to find the eigenvectors. For lambda is equal to minus 1, we Ax, okay, I put minus 1, Ax is equal to lambda, right? So I have two variables, x1 plus 3x2 minus x1, 4x1 4x1 plus 5x2 equal to minus x2. This implies 4x1 plus 6x2. So this is basically the same equation, right? So you are getting some redundant equation. So that means that from here we will be getting x1 by 3, x2 by minus 2. I take some constant c, some real number. So then my eigenvector will be eigenvector I will not write c minus v1, right? And similarly, you just check for the other one. What is that? So here we can see that corresponding to, you just check compute what is the eigenvector corresponding to 7, and then you see that they will be actually linearly independent eigenvectors. So corresponding to 2 eigenvalues, you will be getting two independent eigenvectors. Okay, but this may not be the case for all the time. This may not be the case. Like your corresponding to a determinant, you can find the eigenvalues for which both the eigenvectors will be dependent. So it will not for here you are getting the 2 eigenvectors which are linearly independent, which will be spanning the whole space R2, the space R2, but we can get some eigenvectors which will be just spanning only a line. Okay, so there could be some variation of the eigenvectors what we will be getting. Okay, so let's see a couple of properties which we will be using. The Kelly-Hamilton theorem is kind of a side result. We'll not be using this result in our main theorem. So I'll just skip this. So only thing is that you just note that when you substitute your matrix A in that characteristic polynomial, so it will satisfy the equation, the matrix equation in that case, right? So right hand side will be the zero matrix. Okay, so that's the Kelly-Hamilton theorem. Okay, so I think I'll not go for the proof. Most of you have already seen those properties of eigenvalues and eigenvectors, but I need to use some of the properties. As I was saying that to each eigenvalue of A, there exists at least one eigenvector. Is it easy to prove? I think it's simple, right? How to prove that? You just go to this. So suppose lambda is an eigenvalue. So then what? If lambda is an eigenvalue, then we have this. It will satisfy this characteristic polynomial or characteristic equation. So then we have this determinant of A minus lambda I equal to 0, right? So when this is true, when determinant of A minus lambda I true, so we think about this homogeneous system A minus lambda I x. This will have some non-zero solution. And that will be our eigenvector. So corresponding to each eigenvalue, there exists at least one. So when you have one eigenvector, you can multiply with different real number, you will get at least many eigenvectors, right? So that's why eigenvectors are not unique corresponding to an eigenvalue. Corresponding to an eigenvalue, basically you will be getting a space, a subspace. So that's the characteristic subspace generated by those eigenvectors corresponding to an eigenvalue. Second one, to each eigenvector A, there exists unique eigenvalue. Eigenvalue corresponding to an eigenvector is unique. So let us see also this very simple. So suppose that corresponding to one, so we have to show that suppose there are two eigenvalues corresponding to one eigenvector. So then what? So suppose lambda 1 and lambda 2 are the two eigenvalues corresponding to one eigenvector, say V. V is lambda 1 into V, V will be lambda 2 into V. Okay. So this implies what? This implies your lambda 1 minus lambda 2 V equal to 0. 0 vector, right? But V vector is non-zero because this is an eigenvector. So lambda 1 must be equal to lambda 2. Since V vector is not equal to 0, lambda 1. Okay, you try those proofs of these properties. I'll just keep if A be a singular matrix, then 0 must be an eigenvalue. If A be a non-singular matrix and lambda is one of the eigenvalue, then lambda inverse is one of the eigenvalue. If A, B are two matrices of same order, then A, B and B have the same eigenvalues. These are simple properties. You need to just use the definition of the eigenvalue eigenvector and do little bit of reduction, you'll get it. Instead, I'll just go to the last proof, the last property. If x1, x2, xr are R eigenvalues of an n by n matrix A corresponding to R distinct eigenvalues lambda 1, lambda 2, lambda r, then x1, x2, xr are linearly independent. So corresponding to distinct eigenvalues, if we have say eigenvectors v1, x1, x2, xr, then these are linearly independent. So this is a nice property. We need to use this in the diagonalization. So that's why I'm a little bit interested in proving this. Although I will not go for the proof for till R, maybe I just prove it for two vectors. Yes. It should be eigenvectors. Yeah, you're right. So it should be eigenvectors corresponding to lambda 1, lambda 2, lambda n distinct eigenvalues. So how to prove it? If we are given only one, so that's independent. Right? So that's not. So suppose we have we consider two eigenvectors corresponding to two distinct eigenvalues, say x1 and x2. x1 and x2 are two eigenvectors corresponding to say lambda 1 and lambda 2, lambda 1, lambda 2. What we need to prove to show that they are linearly independent? So if we take a linear combination of these two vectors, c1 into x1 plus c2 into x2 equal to 0 vector, then we have to show that the only possibility is c1 equal to c2 equal to 0. Yeah. So it's also not very difficult. So you can write, so these are the eigenvectors. So we have already a of x1 equal to lambda 1 x1, a of x2 lambda 2 x2. So we take a linear combination, say c1 x1 plus c2 x2 equal to 0 vector. You somehow you express this with respect to only x1 or only x2, and then you show that the coefficient vanishes. Okay. You just multiply, maybe you just multiply this with c1 a. You just multiply this with a, x1 plus c2 a x2 equal to 0 vector. So then you substitute these two. So this is my and this is 3. So we substitute AX1 by C1 lambda 1 X1 plus C2 lambda 2 X2 equal to 0. Then you again substitute from 3 say C2 X2 C1 lambda 1 X1. We substitute from 3 C2 X2 is minus C1 X1 equal to 0. So this will give you lambda 1 minus lambda 2 into C1 into X1 equal to 0. Since C1 not equal to 0, oh no, sorry, lambda 1 not equal to lambda 2 because we have taken distinct eigenvector values, and X1 is eigenvector, it also cannot be 0 vector. So only possibility is C1 equal to 0. And then you substitute it in 3 and you will get C2 equal to 0. Okay, so this implies that X1, X2 are linearly independent. Similarly, you can extend this for 3 vectors, and in the end, using induction, you can prove this is true for R number of vectors. This is an important property. Okay, so one more definition. So before the diagonalization, the final step. So two matrices are similar. Okay, a matrix A is said to be similar to a matrix B if there exists a non-singular matrix P such that B equal to P inverse AP. Okay. So this is a definition. We say it's similar because there are many properties will remain preserved in A and B. For example, if you take the determinant of B, you just see that it is immediately determinant of A, because determinant of P and P inverse will be cancelled, right? So determinant of B and determinant of P, if they are similar, they are same. Similarly, we can show that the eigenvalues will also be same for the matrix B and matrix A. Their rank will also be the same, and the number of independent eigenvectors will also remain same. Number of independent eigenvectors, because their eigenvalues are same. So if they are distinct, some of them are distinct, so we'll get the distinct vector, independent eigenvectors. Just one example, you can take that although we said that for the similar matrices, these properties will remain same. The eigenvalues, determinant, trace, rank, number of independent eigenvectors. If for the matrix A and B, although they have the same eigenvalues and the same determinant, they are not similar. They are not similar because here we have taken one matrix A, which is the identity matrix. So when you consider the identity matrix, then you just consider any 2 by 2 non-singular matrix. You multiply with that, you will see that this will be the same matrix. So identity matrix is similar only to the identity matrix, but the other matrix B is not identity matrix, right? So that's why these two are not similar, although they are. So it's the converse is not true. Whatever we have said, the property in the properties. Okay. So now we define the diagonalizability of the matrix A. So using the similarity matrix. So the matrix A is diagonalizable if A is similar to a diagonal matrix. Matrix A is diagonalizable if A is similar to a diagonal matrix. That is, there exists a non-singular matrix P. If you multiply with that matrix P inverse B P, so then you will be getting the matrix A. Okay. Or the other way around. If you just multiply with the matrix P inverse A into P, so you will be getting a diagonal matrix B. Okay. So both way it is true. So then if the matrix A is diagonalizable, then we can, from the previous property what we have just stated, we can say that the matrix A will have the eigenvalues as the diagonal elements, because both of their eigenvalues will be same, and for a diagonal matrix the eigenvalues will be the diagonal elements. That's a very simple property, you can just check. The diagonal matrix will have the eigenvalues at the diagonal elements. So if the matrix A is diagonalizable, so the eigenvalues of the matrix A immediately are coming from the diagonal elements of the diagonalized matrix. Now, here is the most important property which will give us some idea of how to do the diagonalization for higher dimension or so any dimensional matrices. So first we want to see that how we can do this for the square matrix. This property, so you want to see if an n by n matrix A has n independent eigenvectors, we are saying that n independent eigenvectors, then A is diagonalizable. So the matrix A is n by n. We are saying that it has some independent eigenvectors. We are not giving any condition when it will have independent eigenvectors. We are just saying that the matrix A has independent eigenvectors, xi1, xi2, xin. These are my independent eigenvectors. So what we have now, we apply this matrix A on this xi1, so we are getting some lambda 1 into xi1. Lambda 1 will be unique, right? Lambda 1 will be unique. So we cannot have lambda 1 and lambda 2 cannot be the same, corresponding to two different. So that we have already proved. A xi2, lambda 2 xi2, and A xin equal to lambda n xi. Okay. So we are taking n vectors. We have now found n vectors from Rn, and they are mapping for the square matrix. In case we are able to find these n independent eigenvectors corresponding to a matrix, so then we have the explicit mapping between those vectors and their images. So these are say in this Rn, and their images are also in Rn because we are considering only square matrices. So all these we are finding the action of A. So xi1 is going to lambda 1 xi1 and so on. Xin is going to lambda n xi. Right? For a square matrix, both the this domain space and the range space are the same, right? So basically this mapping we have found, and if we are able to find this kind of mapping, it's simple to check that how to express this matrix A as a or write it in terms of the diagonalization of the matrix A. So we can write the column vectors as A xi1, A xin, xi2, A xin, right, equal to lambda 1 xi1 to lambda n xin. So what is this? I construct the matrix P as the column vectors xi1, xi2, xin. So my P is this matrix xi1, xi2, xin. So you can write this okay, right? AP will be giving me this matrix, and what about this one? What about this one? So I write the diagonal matrix as lambda 1, lambda n, right? And we'll be multiplying this with one column vector will be What should I write? I should write this P into D, right? So this is my P. So if you take so the rest are 0, right? So you'll get this this implies this basically. So this implies this is my diagonal matrix. So what is then we can write A equal to so A equal to P diagonal matrix, right? For the square matrix, it is we can just for only for from by this observation we can just get the diagonalization of the matrix, right? So what is the key here? I mean, how we are able to find it? Because we have this relationship A is I1 equal to this lambda I1 or all the linearly independent set of vectors and their mapping we have. So since these I1, I2, In are independent in Rn, so these are the basis vectors in Rn. So these are the basis vectors in Rn. Similarly, you can show that this lambda 1, I2, I1, lambda n, In are the basis vectors of Rn. Okay. So we have a mapping between the basis vectors of Rn to basis vectors of Rn, and then we are able to write it. Now, what we need to do, we have to generalize this for a general matrix of dimension m by n. So then the idea will be to find those basis vectors from Rn and Rm and to relate them. Okay. Okay. Before that, we just want to discuss a little bit about if we have taken that in independent eigenvectors of the matrix A. When it is we are able to find n independent eigenvectors, we have just seen one property number 10. So when all the eigenvalues are distinct corresponding to this, right? So when all the eigenvalues are distinct, we can find n independent eigenvectors. But that may not be the case all the time corresponding to a square. So what we should do then? So basically, lambda could be coming multiple times. So that's the kind of bottleneck. So what we should do in that situation? So it is not always possible to find n independent eigenvectors corresponding to a matrix. So that is one thing you should consider. I mean, but in some cases, even if lambda is repeated say m times, if we are able to find m eigenvectors, then we'll have full set of linearly independent eigenvectors corresponding to Rn, right? So then we are able to diagonalize the matrix, right? So in that case, we are able to diagonalize. So whether lambda is repeated many times or only once, then we are able to find n independent eigenvectors and we can diagonalize. But if it is repeated, so then we have to check two kinds of multiplicity. So basically, we are suppose lambda is repeated 3 times. Okay, so then we say that algebraic multiplicity of lambda is 3. Okay, then we see that what is the dimension of this null space of A minus lambda I, from which we are finding the eigenvectors. If the dimension of that null space A minus lambda I is also 3, so that's the geometric multiplicity. So then we say that lambda is regular. That means that we are able to find the 3 independent eigenvectors corresponding to that lambda, and we can find total n number of eigenvectors for the matrix A, and we are able to diagonalize, right? So when lambdas are all distinct, we are always able to find n independent eigenvectors. When some of the lambdas are repeating, say m times, then we have to see what is the dimension of the null space of A minus lambda I, from where. So are we able to find m independent eigenvectors corresponding to that particular eigenvalue? If yes, then our lambda, that particular lambda is regular. And if all the lambdas are regular corresponding to a matrix, we are able to find the n independent eigenvectors and we can diagonalize the matrix. So that's the rule you have to follow. But there will be some examples where you can see that corresponding to one lambda, even if it is repeating say 3, so the eigenvectors corresponding to that particular lambda 2. So in that case, this is not equal. We are not able to find the complete set of linearly independent eigenvectors. We cannot diagonalize. So for example, one example I think I have. So for the first example, if you consider this example A is 1031, so this is not diagonalizable because you can see that here lambda 1 has 2 times repeating the eigenvalue, right? But its geometric multiplicity, that is the number of eigenvectors you can find corresponding to this lambda, is 1. You cannot find 2 independent eigenvectors corresponding to that particular lambda. So that's why it is not diagonalizable. You can try few of the exercises. So just move on. Okay, to understand little bit more about this diagonalization of the square matrix, so we consider now the symmetric matrix. So symmetric matrices are considered the nicest matrices in linear algebra. This will have always the most beautiful properties, and we will be also using in the applications, mostly with the symmetric matrices. What other matrices cannot satisfy, this matrix mostly can satisfy. Okay, like I was saying that for general matrix A, you may not have all these n independent eigenvectors, but for the symmetric matrix, it will always have the n independent eigenvectors. Okay. So few of the properties you can try with nice properties. I was also saying that when we consider the characteristic polynomial corresponding to a matrix, the eigenvalues may not always belong to the real number, right? It can be also complex number. For example, you can also consider that orthogonal matrix. I think the rotation matrix as cos theta minus sin theta cos theta. You just check that the eigenvalues are complex numbers. Okay, and also its eigenvectors will also be in the complex space. Okay. So, but for symmetric matrix, we can prove that all the time the eigenvalues are real numbers. The eigenvalues are real numbers. And the second nice property is that the eigenvectors corresponding to two distinct eigenvalues, we said that they are linearly independent that time, but here they are orthogonal. So the nicest property what we can find. Okay, so they are orthogonal. If we consider the symmetric matrix and consider two distinct eigenvalues, so corresponding to that, the eigenvectors will be orthogonal. Okay, and we have seen how nicely we can compute the projection and other thing using the orthogonal set of vectors. So these properties you please try yourself. So the third property, what I was saying, that corresponding to each eigenvalue of the symmetric matrix, its algebraic multiplicity is same as the geometric multiplicity. That is, if lambda is repeated say 2 times or 3 times, similarly you can find 3 independent eigenvectors corresponding to that particular lambda. So then you will always have the full set of not only linearly independent, you can also convert them to orthogonal set of eigenvectors. Okay, so the symmetric matrices are always diagonalizable. Not only that, we call them the orthogonally diagonalizable. I haven't written this here, but this is called the orthogonally diagonalizable. That means that you can construct this matrix P by considering the n orthogonal vectors, n orthogonal eigenvectors, and you can also divide by the unit length, of those the length of those vectors, by which you will be getting n independent n orthonormal eigenvectors. So then your P will be orthogonal matrix. So I denote this by Q. So in that case, you do not need the P inverse. It will be the Q transpose. Right? For the orthogonal matrix, the inverse is actually equivalent to the transpose operation. So you can compute for the orthogonal matrix, you can compute the inverse by its transpose. So you can write then this matrix A equal to Q D Q transpose. So these are the nice properties of the symmetric matrix we want to use in our singular value decomposition. So this is the this is called the spectral theorem. What I was just saying, that every symmetric matrix A has the factorization A equal to Q lambda Q transpose with real eigenvalues in lambda and orthonormal eigenvectors in Q. Okay, so so from here just one point you notice that when we can write A is equal to Q A Q transpose, you can also express this as the sum of those terms lambda 1 into P1, lambda 2 into P2, lambda n into Pi. Okay. So what are those Pi's, capital Pi's? These are the what will be this Q1 into Q1 transpose? This is a so we discussed also this thing in the last lecture. If you remember, when you are taking when you are multiplying a column vector with a row vector, we are getting a rank 1 matrix. We are getting a rank 1 matrix. It's not a real number. So this capital P1, capital P2, capital Pn, which are basically Q1 into Q1 vector and Q1 vector transpose, these are the rank 1 matrices. So we have these orthogonal directions Q1, Q2, Qn, right? And then P1, P2, Pn are the projection matrices along those directions. Projection matrices along those directions. Okay, so those are the rank 1 matrices. We have discussed this when we discussed the projection along a line, right? So you remember that there it was capital P was A1 A or A transpose by A transpose A. A transpose by A transpose A, where A transpose A here is the length 1 because these are the orthonormal vectors. Okay, these are the orthonormal vectors, so denominator will be 1. So the other part will be this Q1 transpose, which are the rank 1 matrices.